Water treatment plants have come a long way in the past couple decades. However, stuff still slips through the cracks. Dozens of household products and personal items, from medications to fragrances, are sneaking past the system, harming aquatic life and surrounding ecosystems. Scientists at the University of Manchester may have cracked the code with a tiny invention that acts like a molecular jail, locking dangerous chemicals away before they can do harm. Could this breakthrough reshape the future of clean water? Check it out! Dr. Imogen Rydell, a Royal Society University Research Fellow at the University of Manchester, states, "While domestic wastewater passes through wastewater treatment plants, these plants frequently do not meet the capacity or level of chemical purification required to completely prevent medicinal and healthcare products reaching our ecosystems. Medications that are unmetabolized pass through our bodies, along with chemicals from households, as well as hygiene and personal care products, making their way down our drain and into our waterways. This seemingly invisible pollution source has become a growing issue in recent years. Studies suggest that these chemicals potentially pose a danger to animal health and welfare when present as an environmental contaminant, and even pose a risk to humans. Once in our waterways, these chemicals bioaccumulate in the fatty tissues of aquatic organisms, resulting in negative effects on their physiology, development, and even reproduction. A compound commonly found in female contraceptives, ethinyl estradiol, has been shown to enter our waterways through the excretion of unmetabolized medication into domestic wastewater and has been implemented as a cause for the feminization of male fish. In addition, a common synthetic chemical found in fragrances, laundry products, and soaps, called tonalide, has also been shown to enter our waterways, causing harm to surroundings, physiological changes, as well as reproductive and developmental problems. A big factor as to why these substances aren't being removed via traditional water treatment plants is their water-repelling or hydrophobic attributes, a key feature that makes this new form of technology so effective. Enter the metal organic cage, or MOC. While this technology has been used in the past to capture, store, and release pollutants such as chemical warfare agents and potent greenhouse gases such as sulfur hexafluoride, side note, 1 kilogram of this stuff is equal to 22,000 kilograms of carbon dioxide equivalent. MOCs are made up of metal ions, forming a pyramid, linked together by organic molecules, creating a hollow space in the center where pollutants are captured. In aqueous environments, and by implementing these new techniques, water-repelling compounds can be trapped inside this space too. This capture occurs through an effect known as hydrophobic binding. Due to the poor water solubility of what was essentially the glue of this structure, panel ligands, MOC technology was not often applied to aquatic-based systems. However, thanks to this new research, those limitations may be a thing of the past. Previously swapping out ligands, or glue, to a water-soluble form led to a weaker and less stable structure. However, researchers found that incorporating sulfonase-based ligands into their MOC structure proved effective, maintaining structure, capturability, and water solubility. Nevertheless, these dream sulfonase-based ligands are hard to come by. That was until researchers found an alternative, easily adaptable synthesis technique. Through nuclear magnetic resonance spectroscopy, analysis of the molecular structure was conducted and confirmed that the new form of MOCs are able to capture and ultimately remove unwanted pollutants in its hollow cavity, including estradiol, ethinyl estradiol, testosterone, progesterone, tonalide, and cholesterol. Future efforts are set to not only create different size binding pockets and design specific functions for MOCs to maximize utility and applications. Efforts are also focused on developing a recycling protocol for this MOC system, creating an immobilized version where wastewater flows over the MOC, extracting pollutants. The MOCs could then be regenerated or emptied via appropriate organic solvent. This new technology holds the potential to not only provide safer, clean drinking water, but to also address the increasing problem that is faced by sensitive habitats and delicate ecosystems within these waterways, as well as those that surround them, protecting biodiversity and delicate habitats for future generations.